Hello. In this video, we are going to introduce the concept of the density of states, and we are going to discuss how this function can be calculated via the explicit enumeration techniques that I've introduced in other videos. Before we get onto that, however, let's take a moment to visit the grave of the father of statistical mechanics, Ludwig Boltzmann. On this slide, you can see a picture of Boltzmann's grave. Two things strike me whenever I see this picture. The first is that Boltzmann had absolutely enormous shoulders, but perhaps that was an artistic choice. The second thing is that the only thing on the headstone is the equation S equals K log W, which is a pretty cool tribute to the very smart guy who transformed our understanding of physics by developing this equation. So what is this equation? Well, just in case you can't read it from the grave, the equation reads S equals K log W. I've written ln here as we're taking the natural logarithm. In this equation, S is the entropy. The K is Boltzmann's constant. The W is then the number of microstates. To understand this equation, you have to see how it provided a way of understanding what entropy was. To be clear, Boltzmann did not develop the concept of entropy. Other researchers had seen that it was necessary to introduce an extensive thermodynamic variable called entropy in their thermodynamic theories. What Boltzmann did by introducing this equation was provide us a way of understanding the physical origin for this quantity. He gave us a way to calculate entropy. I think the importance of this equation is clearer if we discuss how we might use Boltzmann's famous equations. I have introduced a second version of the equation here. In this version of the equation, I have chosen to write S as a function of E. I am thus asking what the entropy is as a function of the energy. Using Boltzmann's equation, it is easy to determine what the entropy as a function of energy is. We just need to count the number of microstates with each energy value. The symbol omega E that we have introduced here thus simply counts the number of states with energy E. And from this, we can get the entropy as a function of the energy. Let me put this another way. To calculate the entropy as a function of the energy, this equation tells us that we just need to count the number of microstates with each energy E. The count of the number of microstates with each energy E, omega E in this expression, is the quantity known as the density of states. This all sounds relatively straightforward, but how is it done in practice? Can we write a Python script to compute the density of states? The answer is obviously yes, so let's talk about how we can go about doing this for the simple lattice systems we have been looking at in this module. For the sake of argument, we will consider a system of particles that can each be in one of two states as shown here. We will say that a particle in the up state has an energy of 1 and a particle in the down state has an energy of -1. We will suppose that we have 8 such particles in our system. Once we know this information, we can work out the highest and lowest energies that the system can take. The system will be in the highest energy state when all the particles are in the highest energy state that they can be in this case, the +1 energy state. The highest energy state of the system thus has an energy of 8. Similarly, the system has the lowest possible energy when all the particles are in the ground state. The energy of the ground state for a particle, in this case, is -1, and the energy of the ground state for the whole system of 8 particles is thus -8. All the other states that the system can be in will be between these lower and upper bounds. Furthermore, you will always get an integer if you add two integers together, so we know that the energy must take an integer value. We can thus begin our code for calculating the density of states by creating an array with 2 to the 8 plus 1 elements as shown here. Ultimately, the 0th element of this array, of this vector, will contain the number of states with an energy of -8. The first element will contain the number of states with energy -7. The second, the number of states with energy of -6, and so on. We can then write in our code a loop over all the microstates, like this one here. We are once again using our trick of generating the binary representations of the numbers between 0 and 2 to the 8 minus 1 to generate all the microstates that the system can adopt on this line of the code here. We are then calling a function called Hamiltonian to calculate the energies of these states. This is done on the line indicated by the black arrow. Now, however, rather than computing the contribution to the partition function or ensemble average, as you would have done in previous exercises, we determine which element of the density of states array we will need to add this microstate to. This is what is done on this line here. The first step in this procedure is to add 8 to the energy. The value for ibin, the variable ibin, for a configuration with an energy of -8 will thus be 0. The value of ibin for a configuration with an energy of -6 will be 2, and so on. We can thus ensure that element 0 of the variable DOS will contain the number of states with an energy -8, element 1 will contain the number of states with energy -7, and so on. Notice that we also need to convert the energy to an integer here. The elements of our array, DOS, are referred to using integers and not real numbers, which is why we need to use this int function in these two lines of code. Once we have done this, we can safely just add 1 to the element of the variable DOS that corresponds to the energy of the current microstate, to signify that we have found another microstate with this particular value of the energy. The final part of the code that we need is the part shown here. This bit just makes a plot of the density of states. The first command here, the one that uses the np.linspace, ensures that the values for the points in the graph are plotted at the various energy values that the energy takes. The final result from this code is a bar chart that looks like the one shown here. This has energy on the x-axis and the number of states that have that energy on the y-axis. You can clearly see that there are many states in the middle of the range of energy values and much fewer states that have extremal values for the energy. I hope that should be enough to get you through the next batch of exercises. Have a try and see if you can make your own density of states plots. For now though, thanks for your attention and good luck.